Hi, I'm Geraldine, and I'd like to present to you a systematic approach to deciphering a random whittle workflow that you found on the street. I'm first going to talk a little bit about why this is even a thing. Then we'll dive into some real-world code examples. As a caveat, I will be using examples from genomics specifically, but I promise there will be enough file format related tomfoolery to appeal to all bioinformaticians. So, just so we're on the same page, WDL, or WDL, stands for Workflow Description Language. As its name suggests, it is a language for describing workflows. It was originally created at the Broad Institute for running the Sequencing Center's main genome processing pipeline, but since then it's been adopted by a variety of groups, and it has become an open standard stewarded by a community organization called OpenWDL. WDL is designed to be highly portable across different platforms. It supports scalable execution on the cloud particularly well, and it aims to be user-friendly for people with limited programming experience. And what I want to emphasize here is that there's a pretty rich ecosystem of WDL workflows out there, covering a wide range of analysis use cases that are just begging to be reused. And in particular, quite a lot of these WDLs come from large consortium projects and have been engineered to be very robust, both technically and scientifically. And so there's a ton of value to be gained from being able to reuse them, either as is or with whatever amount of customization makes sense to your project. So the premise of my talk is that you come across a WDL workflow, maybe from reading a paper, browsing a workflow repository, or someone handed it to you with minimal to no explanation. And you think it might be useful to you, but you're new to WDL and you'd like to be able to figure out an intermediate amount of detail about what it does without having to actually learn the whole language. And note that I say intermediate amount because you want to know more than just it does variant calling. But at this early stage, you also don't need to know the meaning of every line. So the Goldilocks amount of information, not too little and not too much. Speaking of which, quick shout out to local UW-Madison researcher Chao Li, whose Play-Doh Goldilocks illustration made the journal cover for their recently published paper on cell culture engineering, which is just outstanding use of media in every sense. Anyway, I regularly run into a version of this problem of discovering a random WDL because I do a lot of blogging about other people's projects and pipelines, and I like to poke around under the hood before I start writing. And so I developed a little method that's kind of embarrassingly simple, yet it's quite effective at answering the two key questions I always have. Number one, what are the main steps in the workflow? I.e., what operations does it perform on the input data? And number two, what is the flow of operations? Meaning, is there any flow control logic like conditional statements, parallelization, etc. that I should be aware of? Number three, I'm not off by one. What compute resources does this require? I'm not going to cover here. It's an important question, but the answer is very dependent on the workflow author. So it would take a whole other talk to cover that. So maybe a topic for next year. In the meantime, let's tackle 1 and 2. So here are the 5 steps I propose to answer these questions. And let me just say, congrats on completing step 1. But really, first, you are going to have to learn a tiny bit of WDL, the equivalent of learning how to ask for the bathroom when you go to a sufficiently foreign country. I will teach you this shortly. Next, you're going to use a utility tool to create a visual representation of the workflow graph, which is honestly 5% of the total time you're going to spend on this, and it's going to deliver probably 80% of the answer you need. Then, using the graph diagram as a guide, you're going to identify what are the workflow steps and look up specific bits of code to determine the flow logic that connects them. And finally, you'll usually want to dig a bit deeper into specific elements on a case-by-case basis. So, here is the 10,000 meter view of WDL structure. At the top level, there are two kinds of code block: the workflow definition block and any number of task definition blocks. Tasks describe individual steps. One task block is like a wrapper for a given command line. And the workflow is where we call those tasks to operate on specific inputs and add whatever additional control logic operators are needed. Variables can be defined and manipulated at several levels, but you don't really need to know too much about that up front. Just know that you can take the output of one task and explicitly assign it to another task as input. And that's how the WDL execution engine will know what order to run things in. The command block in a task definition can accommodate mostly anything you would run in a shell, including pipes, multi-line scripts, and so on. It's up to the workflow author to decide when to group the execution of several tools into a single task versus separating them out into individual tasks. And here is an example of a complete workflow description block for a relatively simple WDL that takes in a few input files, including some sequencing data in BAM format, runs a variant calling tool called GATK haplotype caller on chunks of the data determined by genomic intervals, and is run with multiple jobs running in parallel. And then it merges the outputs of the parallel jobs into a single final output file. So if you can pick out the workflow block here on the left and recognize the call statements like call haplotype caller, call merge VCFs, you're actually ready to move on to step 3, generating a visual representation of the workflow graph, which we're going to practice on a mystery workflow. Spoiler, it's pretty related to this one. So let's assume I'm a new grad student. I'm starting a variant calling project, and a departing postdoc sends me a cryptic Slack message with a GitHub link and the instruction, start with this. So, okay, let's check it out. And by the way, I'm going to pretend I'm unable to read any documentation lines because A, sometimes you can't trust those, and B, other times there are just none. So, if you followed the link to GitHub, you could scroll through the entire workflow, but if you're new to WDL, it might feel overwhelming. As much as WDL tries to be user-friendly and succeeds in many ways, there's a level of verbosity in how input variables are declared and passed around that ends up flooding the visual space with a lot of lines that you probably don't care about most of the time. So one way to deal with that is to use an editor with code folding capabilities. But here we're going to see what we can just do looking at the code with minimalist tools. So step 3. Step 3 is the one that requires direct action in this method because it involves running a utility called WOM-tool to output a graph description for the workflow. And running this simple command line outputs what's called a dot file, which describes the workflow graph in the dot language. It's obviously massively summarized compared to the original WDL, but still not terribly human readable. So next, we run this file through a visualization package. And I just use a website called GraphViz Online, but you can run GraphViz locally if you're willing to install something on your laptop, something I have not done since before the pandemic, and my life is better for it. And this is what GraphViz produces from the dot file. You're going to want to pay attention to the different shapes in play here. The ovals represent the call statements from the workflow block. So those are effectively the steps where tasks get executed. Hexagons are operators that control or modify execution. The boxes define the scope of the operators, i.e. what calls are subject to their control. The dashed lines indicate conditional status, meaning there's a conditional operator in play. And finally, the arrows between ovals represent output to input relationships. And so that was step 3. And like I said, this gets us 80% of the way towards understanding what this workflow does. You'll probably have noticed it's basically the same workflow I showed earlier, but with this extra call added. which is under some kind of conditional control. And at this stage, we can sort of read the flow out loud, right? First, if something is cram, call the cram to BAM task, then call haplotype caller using a scatter function, which means parallelize it over intervals, and then finally call merge GVCFs on the output of haplotype caller. And so from here, we can move on to step 4, where we go back to the code and try to match up the elements in the diagram with the corresponding elements in the code. And this part is more labor intensive, and it might not always be necessary to do it for the whole workflow, but I do find it helpful for getting real clarity about how the workflow is really engineered. So I will literally copy parts of the graph diagram and arrange them into a table column format like this. And the reason I do that is because I'm going to copy paste the relevant code opposite each piece of the diagram next, like this. So here I went and looked at the calls, simply using the find function in my text editor or browser, works great. And I copied the relevant code opposite each snapshot from the diagram. And this allows me to make an explicit connection between visual elements like the dash line and the conditional statement, if is cram, for example. Now, if I'm curious about the specific syntax of those controls, I can look up the relevant terms in the WDL language specification on GitHub, which includes explanations and examples of their expected behavior. And finally, I can also see how the calls are connected by their inputs and outputs, as in the case of the merge VCFs call, taking as input the outputs from the haplotype caller call. Of course, the elephant in the room here is the operation of the if is cram conditional statement, which is worth digging into a little further, and that takes us to step 5. So here I use the find function to highlight all instances of the isCram variable that the conditional seems to rely on. And I find a Boolean variable declaration, which makes sense. Clearly, we're testing whether a condition is true or false and adjusting what gets executed accordingly. And so this is a pattern you will see quite often in WDLs, using a combination of substring and basename functions to manipulate file names, generate output file names based on the input name, and in this case, evaluate what is the file type of an input using the file extension as a proxy. And so we're testing whether the input file is a cram file, which is a more highly compressed format for genomic data than the more traditional BAM format. And that makes sense because we want our workflow to be able to process either format without us having to specify it up front. If we're given a cram, we want the workflow to start by converting it to a BAM. If it's already a BAM, skip the conversion, go straight to business. And so finally, whenever you're dealing with conditionals, it's worth checking how the alternative cases are handled downstream. Like here we have to toggle the choice of inputs to the haplotype caller task, which is either the original file if it was a BAM, or a newly generated file if the original was a cram that we had to convert. So more generally, you might also want to drill down into specific task definitions to check what they're doing, what their name implies, or find out what tools they're invoking. But this is the kind of sleuthing you might have to do on a case-by-case basis. And that's about it for single file WDLs. But there is one more thing I want to show you. WDL supports importing WDL code from other files. And so we can make calls to sub-workflows and or libraries of tasks that are spread out across multiple WDL files. We can even import WDL code directly from GitHub URLs. And this is awesome for code reuse, but can make things harder on first approach because you might see something like this with import statements that also assign handles to sub-workflows and tasks, which is called aliasing. And I don't have time to go into the details now, but the good news is if you see this, you can still apply the method we just went over. generating the graph diagram still works. So this is what it looks like when you run WOM tool graph on the top level workflow. And you see the double walled ovals. Those represent calls to sub-workflows, while single walled ovals are still regular calls to tasks. And this is what it looks like if you run WOM tool graph on one of the sub-workflows, which is BAM to GVCF. And if you like, you can practice applying the principles you learned just now to this slightly more complex example. And that's all the time I have for today. I'll leave you with a few takeaways and some links to learn more. First, a picture is worth 1,000 lines of doc strings, so make sure you generate that graph diagram. When you're connecting the code to the picture, focus on call statements and surrounding logic first. Ignore everything else up until the moment where you can't ignore it anymore. Watch out for conditionals, since they introduce complexity in all sorts of ways. And also imports, they introduce complexity, but I will say when you have more compartmentalized code like that, it can be easier to read compared to one massive monolith, because the author already went through the exercise of separating out like functional logical modules on your behalf. So that's the upside. And so here are a few places you can go to learn more. The Open WDL repositories, of course, the specification, the terabyte.bio documentation, which includes some intro materials, plus pointers to how you can actually run WDLs at scale on the cloud using the Tera platform. Then I also included this repository where you can find the code for the workflows I showed you today. I originally described this method in chapter 9 of a book I co-authored with Brian O'Connor, published by O'Reilly in 2020. So this was a first pass at sharing some of that material more widely. If you think this was useful, let me know, and I'll try to adapt more of that chapter in an open format. I'd also love to get feedback and suggestions on how to improve the current material and maybe generalize it to other workflow languages. So thank you for your attention. Good luck with your WDLs.